Good morning, good afternoon, and good evening, everyone. Welcome to Episode 2 of the RTDS Technologies User Spotlight Series 2.0 event. My name is Katie Sidwell from RTDS, and I'll be your host and moderator today. If you're not familiar with our User Spotlight Series, it is a series of webinars. Each one contains 2 user presentations that involve the RTDS simulator. Each presentation is 20 minutes in length, and after both have concluded, we will do a live Q&A session. Today we have 2 exciting presentations that center around renewable energy and microgrid work with the RTDS simulator. And just before we get to those, I have a couple of housekeeping notes to go over. So we encourage you to ask your questions throughout the webinar in the Q&A widget in the webinar tool. We will be responding to your questions in real time via text, and we'll also select a few to go over and discuss a little bit in the live Q&A. Unfortunately, our presenters from the University of New South Wales in Australia won't be present for the live Q&A today due to the time difference, but please feel free to submit questions to them, and I'll do my best to address some of them. Otherwise, we'll make sure that they're answered in our Q&A document, which will be available in the next couple of weeks. We will email that out to everyone who attended the webinar. The recording of this session will also be available perpetually. You can access it either by logging into this webinar tool to view the session, or we'll also upload it to our YouTube channel. And if you're watching it on demand, you can still submit questions. So feel free to use that Q&A widget, and we'll get back to you via email. All right, without further ado, let's get to our first user presentation. The first topic is Grid Supporting Battery Energy Storage System, Modeling and Simulation in RTDS, an Australian case study. And the presenters are Felipe Araño Vargas and Georgios Constantinou from the University of New South Wales. Felipe Araño Vargas is a PhD candidate at the School of Electrical Engineering and Telecommunications at the University of New South Wales in Sydney, Australia. His research interests include the development, modeling, and simulation of inverter-based resources and synthetic grids in real-time digital simulators. Georgios Constantinou is a senior lecturer in energy systems with the School of Electrical Engineering and Telecommunications at UNSW in Sydney. He's also the research and teaching coordinator at the university's Real-Time Digital Simulation Laboratory. Georgios' research covers the areas of power electronics and grid integration of renewable energy, energy storage, and HVDC systems. Please welcome our presenters from the University of New South Wales.
Thank you, Katie. In this presentation, we want to provide some of our insights from our work on grid-supporting battery energy storage systems, and especially the role on power systems with increasing percentage of renewable or inverter-based generation, in general, but also from an Australian perspective as well. Unfortunately, due to some slight delays in the project, we'll not be able to provide all the information we initially planned, but we find that this will have very little impact on our overall conclusions and also in the process we describe for the real-time simulations. Firstly, a very brief overview of our research group. The Real-Time Simulations Laboratory at the University of New South Wales in Sydney is an integrated facility that includes both our simulation and also our power electronics research laboratories at the university. Our research spans from large-scale power system modeling and development of digital twins to small-scale hardware-in-the-loop testing, as for instance our work on bench testing of residential PV inverters and their response to grid disturbances. Now, some context for the project. The size and the remote nature of the Australian power system creates a lot of challenges for the integration of many large-scale renewable energy projects. The area of focus, which is the West Murray Zone and its surroundings, have been notoriously challenging for such integration. The key tasks for our project were to first replicate oscillations that have been experienced in the area, followed by an investigation on how the grid supporting functionalities of batteries can be used to improve different aspects of the power system that we would collectively refer to as system strength. The work that we present here is split into 3 distinct stages, and also has been running in parallel with the commercial part of the project, which is necessary to meet the requirements of the market operator for connection of the battery to the grid. These stages include a proof of concept, which is based on generic models for the inverter and the network, followed by a plant-specific implementation of the OEM solution for the battery, and then a control hardware in the loop testing stage. It should be noted that the intention of this project is to eventually match the model that we run in our real-time simulations with the as-built plant as the project progresses in the form of an area-specific digital twin.
As mentioned by Georgios, the area of interest is the West Murray zone, which is highlighted in light blue in this figure. It expands across part of the states of Victoria and New South Wales, and one of the issues that has been faced in the area are the intermittent power system oscillations, which occur under a variety of conditions. For instance, the figure on the right shows a recorded voltage oscillation that lasted several seconds. Oscillations such as the one presented in the previous slide have been observed on several occasions. Furthermore, they have been seen during normal operating conditions, plant outages, and disturbances. Voltage oscillation may reach 5% peak to peak, and their frequency may vary from 7 to 19 Hz depending on system conditions. Even though the transmission system operator doesn't know the source of the oscillations, the low system strength combined with several inverter-based resources in the area increases the potential of resonance and converted river instabilities, which may result in these oscillations. The challenges in the area have led the system operator to limit outputs of existing renewable generation plants. Moreover, there has been significant delays in new projects as they need to fully assess the impact of the new plant in the area. And once new plants are commissioned, they can also face power output constraints. In the West Murray zone, there is a particular weak area, shown here on the right, that has renewable generation from solar and wind in one transmission substation. Oscillation has also been observed here, and several mitigation measures have been considered to tackle them. Transmission upgrades, synchronous condensers, and grid-scale battery energy storage system are some of the examples. As a first step towards improving the area, a battery project was proposed as it is seen as a more modular and flexible solution. It can provide ancillary and essential grid services while coping with the inherent variability of renewable energy in the area. The single line diagram shows the area we are interested in and where we are going to assess the integration of the battery. The model we developed in RSCAD FX is based on PSSC and PSCAD models and a several number of reports to set, for example, the corresponding operating conditions. We used the embedded conversion tool to convert the model from PSSC to RSCAD. Then we adjusted it and validated the network, its power flow and steady state condition by running a simulation. The modeling of the renewable energy plants and the static power compensators located in the area was based on the generic model for advanced energy conversion system that had been developed as part of these two references. The use of generic model has allowed for a faster development of the model, as it does not require any access to confidential or commercial models available in PSSC or PSCAD. Solar and wind farm, as well as the battery, have been modeled based on digital switching model of a single unit, which current injection to the system is multiplied at the step-up transformer to represent the corresponding power rating. For the battery, we have considered two control operation modes: the grid following mode, which uses PLLs to synchronize to the grid, and the grid supporting mode based on virtual machine technology. In the later case, the battery doesn't use the VLL to synchronize to the grid, but uses the synchronous machine swing equation as reference. For both cases, though, the battery contains reactive power control loop, frequency, and voltage drop controllers. The model we have developed is for PV5 processor cards of the RTDS simulator, and the complete system requires 13 of these cards, which main components are allocated to the hardware as shown in this slide. In order to allow the fast parallel simulation of the system, we split it in 3 subsystems: the weak area, the battery, and the rest of the network. The subsystem containing the battery is simulated in a dedicated rack, and it is connected to the weak grid through a cross-rack transformer. The weak area, on the other hand, is separated from the rest of the network at the single transmission line. This network separation allows the use of separate and interchangeable models for testing different power systems and configurations. Moreover, the approach enables future hardware-in-the-loop testing. It is worth mentioning that 2 different time steps are used to perform real-time simulations. A large time step of 50 micros is used for solving network, static bar compensator, transformer, transmission lines, and control system components equations, and a smaller time step of 2.6 microseconds is used to allow a more accurate simulation of high frequency switching circuits such as the one in the inverter-based resources. The complete model was validated and endorsed by the modeling working group of the project, which includes members from different power system companies. On the left, we have a screenshot of subsystem 1 containing the weak area, and on the right we have part of the runtime environment we have developed as part of the project. In stage 1 of the project, where we consider generic power system components and control models, we were able to observe the positive impact of the grid supporting battery when connected to the grid. In this particular case, before enabling the grid supporting functionality of the battery, the system presents oscillation of 5% peak to peak with a frequency of 9 Hz during normal system conditions. When the functionality is enabled, such oscillations are damped. Furthermore, if we disable the functionality after a period of time, oscillations appear again in the system. Similar results are also observed when moving to stage 2, where we implemented the original equipment manufacturer solution for the virtual synchronous machine emulation of the battery. In this scenario, we are obtaining oscillation after the clearance of a 2-phase to ground fault in the system, and as it can be seen, an unstable operation is reached when the battery is not connected, as well as if the battery is operating under the grid feeding mode. But when the grid supporting battery is connected, unstable operation is reached after the clearance of the fault. Similar results are obtained for different pairs of inertia and damping factor. These results further demonstrate how the grid supporting functionality of the battery helps to maintain the system stable for a fault that causes voltage oscillations in the system. When increasing the power output of renewable generation plants, voltage oscillations are also observed in the system. Even though the frequency is within the range of observable oscillations in the area, their amplitude is much larger and not aligned with previous experiences. This is attributed to the use of generic models and parameters in the network. Nevertheless, as the model and setup used in this case present a worse scenario when compared to what may happen in the real system, it is expected that any analysis and conclusions made based on these results will also apply to oscillation with smaller variation in magnitude. It is also worth mentioning that these oscillations are observed when the battery is disconnected in the system. Additionally, we have removed and disabled protection schemes in the system to allow the operation of other plants. In order to illustrate the role of the battery in the system, we enable its grid supporting functionality at any given time. As it can be observed, when enabling such functionality, oscillations are damped for the range of inertia and damping factor provided by the original equipment manufacturer. The undergoing third stage of the project consists of performing control hardware in the loop when including the controller of the inverter. This additional stage is done as one of the requirements of the funding agency. One option we have is to interface the controller directly to the RTDS simulator through the use of GTAO and GTDI cards. While the GTAO is sending power system measurements to the controller, the RTDS is receiving the fire impulses from the controller through the GTDI card. Alternatively, we can use a multi-vendor approach. In this option, the network model and the weak area are running on the RTDS, while the battery is being modeled in another real-time simulator, in this case a Typhoon simulator. Then the Typhoon is interfaced directly to the controller, which is located in a Typhoon Hill Connect device. For this option, GTAOs and GTAIs are used to exchange voltages at the point of common coupling and the current from the battery respectively between RTDS and Typhoon simulators. We took this second approach to perform some initial tests as the connection between the Typhoon simulator and the Typhoon Hill Connect with the controller was already done and available to us. We first interface the RTDS with the Typhoon simulator and run some simulations. In this figure, we can see the RTDS runtime at the top, the Typhoon scope on the bottom left with some variables, and the model of the battery on the bottom right. In this slide, we are showing the connection of the signals between simulators. It is worth mentioning that analog inputs/outputs of both real-time simulators are in the same voltage range, so we are able to connect them directly. We also exchange some digital signals to trigger the acquisition of data points in both simulators at the same time. Currently, we are waiting for the last firmware of the controller to include it in the setup and close the loop. Here we are showing two simulation results when doing a step change in the active power output of the battery for different sets of inertia and damping factor parameters. The change is performed in the Typhoon simulator, which triggers a plot signal that is received by the RTDS to update the plots, and we can see how the battery changes its output and it affects the rest of the system. To conclude this presentation, I'd like to highlight that targeted actions with suitable investments are required to address current challenges and maintain the secure operation of power systems all over the world. Also, with the increase of inverter-based resources, hardware in the loop testing is becoming more necessary, and some agencies and transmission system operators are already considering this as part of commissioning requirements. For this particular project, we were able to demonstrate that real-time simulators validate the proposed approach for the grid supporting battery in a very weak area of the national electricity market in Australia. In particular, results demonstrate that the battery damps voltage oscillation helping to improve system strength in the area. Finally, the multi-vendor co-simulation approach facilitates the black box modeling and testing of control and protection devices, and we have illustrated its potential by interfacing the RTDS PV5 simulator with the Typhoon simulator through analog digital inputs and outputs. With this last remark, we conclude our presentation. Thank you very much for your attention, and please let us know if you have any comments or questions.
A big thank you to Felipe and Georgios for that great presentation. And thank you to our audience for staying involved with your questions. Please keep them coming. Let's move on to our second presentation of the day. Development of a microgrid controller for a remote off-grid power system in northern Canada and its evaluation using hardware-in-the-loop simulations. Our presenters are Moath Faraj and Atula Rajapakse from the University of Manitoba. Moath Faraj received the BSc Eng degree in electrical engineering from Philadelphia University, Jordan in 2019. He recently finished his master's degree at the University of Manitoba, Canada, and is currently working as a consultant at Quanta Technology. Dr. Atula D. Rajapakse joined the University of Manitoba as an assistant professor in the Department of Electrical and Computer Engineering in 2004, and currently holds a rank of professor. He has a diverse background in power and energy systems related areas. His current research activities mainly focus on power system protection and renewable energy integration. Professor Rajapakse is a senior member of IEEE, a registered professional engineer in the province of Manitoba, Canada, and a fellow of Engineers Canada. He's an active member of a number of CGRE and IEEE working groups. Please welcome our presenters from the University of Manitoba.
Thank you, Katie. Our presentation is on the development of a microgrid controller for a remote off-grid power system in northern Canada and its evaluation using hardware-in-the-loop simulations. I am Atula Rajapakse, a professor at the University of Manitoba. Most of this work was done by my co-presenter, Moath Faraj, as part of his MSc research at the University of Manitoba. I must also acknowledge the contributions of Roshani Kalutantrigi, who is a PhD student at our university. This is the outline of the presentation for today. But before I begin the presentation, I would like to briefly introduce the Power and Energy Systems Research Group of our university. University of Manitoba is the main research university in the province of Manitoba, and it has one of the best power and energy systems research programs in Canada. We have many industry collaborations, including with RTDS Technologies, which is located very close to us in the University Smart Park. University of Manitoba has a strong graduate program in power and energy systems area. Our group has a number of research labs, as listed here, including the Intelligent Power Grid Laboratory, where this work was performed. Intelligent Power Grid Laboratory is equipped with the RTDS Simulator, protection relays, test equipment, and various power system analysis software. We conduct research in three main areas, namely power system protection and automation, wide area monitoring and protection, active distribution systems, and microgrids. If you are interested, you can find more information about the lab at ipowergridlab.ca. Now back to the topic of presentation. There are many remote communities in northern Canada, and they rely on diesel generation for electricity. Many of these communities do not have land transportation throughout the year. Heavy goods and fuel for the whole year are transported during the winter using winter roads that run over many lakes like this. Transportation and storage of diesel poses a hazard to these environments. Accidents and spills can happen, and the cleaning process is very costly. Also, climate changes making the duration suitable for winter roads shorter and sometimes unpredictable. If locally available renewable energy sources can be used for electricity generation, reliance on diesel can be reduced. Among various sources, PV or solar PV has emerged as one of the technologies economically viable. This picture shows an example of a PV system installed in a remote community in northern Canada. However, when the system consists of only diesel and PV, there are some problems. When the load is low and the PV generation is high, diesel generators may have to operate at low power levels, resulting in low efficiency and loss of life. And sometimes when the PV generation is high, we may need to curtail the PV power output to maintain a minimum load level for the diesel generators. So that will make investments on a PV system less attractive. If we add energy storage to the system, it can help improving this situation. Currently, batteries are the most feasible technology for energy storage. In order to get the full benefits of energy storage, a good energy management system is needed. For example, to minimize the cost and emissions while maximizing the use of renewable energy. In addition, battery energy storage system can be used as a grid forming source, making it possible to turn off diesel completely during the periods of low load and high PV output. Typically, an energy management system optimizes the operation over a longer period, such as 24 hours. But we need another type of controller to maintain the stability of the system by ensuring power balance, coordinating the transition between different operating modes, and performing tasks such as secondary voltage and frequency control. We sometimes call this controller as the power management system. A microgrid control system typically has a hierarchical arrangement. The tertiary controller hosts the energy management system, or EMS, and optimizes the microgrid operation over a longer time frame. The secondary controller passes dispatch commands from the EMS to primary level and enforces rate limits, etc. It also ensures the power balance and spinning reserve, which sometimes require performing load shedding. The secondary controller also manages transition between various operating modes. Primary control layer consists of the local controllers. For example, in case of a diesel generator, it is the excitation and governor control. Whereas for a PV and battery energy storage, it involves converter controls. IEEE Standard 2030.7 2017 outlines the specific requirements and tasks of microgrid controllers to help the development of microgrid control system functions. The accompanying standard IEEE 2030.8-2018 describes methods and test scenarios for verifying the conformity of microgrid controllers with the IEEE Standard 2030.7. The possible test methods include purely simulation-based testing, testing using hardware test benches, power hardware in the loop testing, and control hardware in the loop testing. Among these test methods, hardware in the loops testing, which include both power hardware in the loop testing and control hardware in the loop testing, is the most flexible and cost-effective method. Hardware in the loop testbeds can facilitate faster and more accurate design iterations. Compared to actual physical tests, this method saves engineering time and cost. Hardware in loop test in conjunction with controllers allow the testing of control algorithms to verify that they comply with IEEE standards. Any microgrid control design needs to be customized to the given system. This is especially important when the system is an isolated grid. Most of the published information on the development and testing of microgrid controllers, particularly secondary controllers or power management systems are for microgrids connected to stiff systems. Therefore, in this research, we developed a microgrid power management system for an isolated power system with PV and diesel generation augmented with a battery energy storage system. Then we developed a control hardware in the loop testbed to evaluate the control performance. The methodology involved 5 steps. In the first step, we developed a real-time simulation model of the microgrid. In the second step, we developed the algorithms for power management functions based on the identified requirements. And then we implemented these algorithms on the real-time simulation model. In the third step, we validated the models and control algorithms using real-time simulations. In the fourth step, we implemented the power management functions on a hardware device and interface it with the real-time simulator. So this formed the controller hardware in the loop simulation testbed. In the final step, we conducted various tests to validate the controller performance. With that, now I am passing the presentation to Moad to complete the rest.
Thank you, Professor, and thank you, Katie, for organizing. This is my microgrid test system. It consists of a diesel plant, battery energy storage system, and a PV system, and a set of balanced loads. The diesel plant operates in an isochronous mode if one diesel generator is in, where if 2 diesel generators are in, a droop mode will govern the operation of the diesel plant. The PV system is interfaced through a boost converter that regulates and maximizes the PV output power, and VSC that operates in a grid following, and LCL filter, whereas the battery energy storage system is interfaced through a buck boost converter to facilitate a bidirectional power flow and regulates the DC link voltage. The VSC of the battery energy storage system operates in a grid following mode when the diesel is in, and it's called generator support mode, GenSup, whereas if the diesel is out, it's considered islanded mode, and the battery energy storage system starts forming the voltage and frequency for the PV VSC. The energy management system usually accommodates resource management and planning tasks over longer control horizons, usually expanding hours to days. The energy management system deployed uses an optimization framework to obtain the minimum daily cost and emissions. For the considered control horizon, the derived optimal operational plan suggests the power commands for the 2 diesel generators along with their on and off status, the hour hourly commands of the battery unit. And to compensate for the unanticipated events and unforeseen deviations occurring in the predicted data, the energy management system adjusts the derived operational plan using a receding horizon model protective control. IEEE 2030.7-2017 standard states the dispatch and transition functions as the core level functions of a microgrid controller. Dispatch function balances the power generation and demand under various operating conditions, redispatches the ARs according to the changes in load and generation, and follow the optimal operational plan suggested by the tertiary level control. Whereas the transition function manages transitions of the microgrid, such as reconnection, planned islanding, and unplanned islanding, and switch the dispatch functions into different operating modes. The dispatch strategy formulated under the guidance of the IEEE standard integrates the following optimum control signals coming from an optimization framework, start and stop signals for the diesel generators, and the battery energy storage power reference. A blue color code is used to mark these signals. The dispatch strategy is based on a set of constraints summarized in Table 1. For the battery energy storage system, there is a state of a charge limitation. The SUC has to be between SUC minimum and maximum, and active power limitation. For the diesel plant, the diesel power has to be higher than 30% of the rated power to increase the fuel efficiency, and less than the rated power. Whereas for whereas the system has always to have a reserve generation capacity to deal with the random nature of PV and load, which is a function of the load and PV power. A detailed flowchart for the dispatch functions were developed. For generator dispatch, when the diesel is on, we will start by the emergency check. If emergency is off, then the power management system will follow the energy management level signals for the diesel plant. Whereas if the emergency is on, the power management system enables the diesel plant that satisfies the load and reserve while charging the battery at a very low power. Then the power management system will request an updated operation plan from the energy management signals. If the power management system receives an updated operational plan, this will be marked as emergency off situation and the energy management level signals is being followed again. As long as there is no updated operational plan from the energy management level signals, the power management system is mainly responsible for enabling the diesel units. Then, based on the S2C, we have three different cases. Case 1, when the S2C is less than S2C minimum, you will minimally adjust the battery energy storage power reference to charge it at a very low power and check the loading of the diesel unit. If the diesel unit is highly loaded, this will be marked as emergency on situation. Case 2, when the S2C is between S2C minimum and S2C maximum, the battery energy storage system is mainly responsible of maintaining the minimum loading of diesel unit, as can be derived using this equation. Whereas if the S2C is higher than S2C maximum, then the battery is pushed into idle state and the PV unit is mainly responsible of maintaining the minimum loading of diesel unit by curtailing its power. Out of these three cases, the derived power reference will be provided to this equation that will maintain an adequate reserve in the system. Then we will go through emergency check again. If emergency is off, the energy management level signals is being checked again to know whether or not to initiate a planned island transition. If not, or the emergency is on, this loop will be executed again. For the islanded dispatch, where the diesel is out of operation, we have 4 different scenarios marked by the numbers from 4 to 7. When there is a surplus PV power and the battery is not fully charged, then the battery energy storage system provides the required slack power. Whereas, if we had an excessive PV power generation for a sustained period and the battery becomes fully charged, the PV unit will enter a limited power mode and start tracking the load in order to push the battery into idle state. Whereas if we had a high load and relatively low PV and the diesel in this case is unavailable, then a power reserve scheme is applied to maintain an adequate reserve to shed non-critical loads. And also an energy reserve schemes can be applied to prolong the system operation, in which when the S2C falls below a certain threshold, a set of loads can be interrupted. Where if we had a sustained period of high load that causes the S2C to fall below S2C minimum, or the power reserve is violated, then the system will turn on emergency mode and override the energy management level signals for the diesel unit and start the diesel plant. And each time this loop is executed, we will start by checking the energy management level signals to know whether or not to start the diesel plant. For planned islanding transition, once we receive a planned islanding signal, we will start by unloading the diesel plant by increasing the power set and the Q set of the battery energy storage system. Once the diesel plant is unloaded, we will open the diesel breaker and enable islanded dispatch. For the reconnection transition, once our reconnection signals are received, we will start by turning on the active synchronization scheme of the diesel plant and measure the voltage and frequency across both sides of the circuit breakers. When the voltage and frequency and the phase angle are within a certain limits, we will close the circuit breaker and enable generator support dispatch. In this research, unintentional islanding events are detected by inspecting the status of the diesel plant breakers. Upon an unintentional islanding, the following is performed. We will start by shedding non-critical loads determined by equation A based on the load priority in order to avoid unnecessary load shedding. And we will switch the battery energy storage control into grid forming control mode and enable island dispatch strategy. For the hardware implementation, we have a desktop running a MATLAB representing the energy management system. It has a forecasting engine and optimization framework to provide the power management system with the optimal operational plan. The power management system is implemented on a real-time automation controller, CHIL RTAG 3350, and interfaced with the real-time digital simulator RTDS through Goose protocol to exchange Goose messages. The RTDS has the microgrid test system and the primary control of the microgrid. This is the laboratory setup. It has a computer, CL RTAG, and RTDS, all connected through a network switch. A human-machine interface is also developed to visually monitor and track the status of the microgrid. The developed control hardware in the loop-based testbed was used to demonstrate the applicability of the hierarchical controller to implement an energy management system over a 24-hour control horizon. This is the optimal operational plan derived by the energy management system, and this is the system actual operation simulated inside RTDS. A good agreement can be seen between the optimal operational plan and the system actual operation. Few scenarios can be detected in the system actual operation. At the 8th hour, we have a diesel minimum loading scenario. In response, the power management system will modify the battery energy storage power level in order to maintain the minimum loading of the diesel one, which is 0.12 megawatt. Here we have a diesel overloading scenario at the 23rd hour. In response, the power management system will instruct the battery to discharge at a higher power. Following a load drop at this point, the power management system instructs the battery again to follow the energy management level signal. We have here results from the 15th hour when the SUC reaches SUC max. When the SUC hits SUC max, which is set here to 99%, the PV power will start tracking the load in order to push the battery into idle state. A 1% dead band can be seen between the limited power mode and MPPT mode in order to prevent the frequent transition between these two different modes. As the SUC reaches the lower band, which is set to 98%, the battery energy storage starts charging again, and the PV now operates at MPPT. However, when it reaches 99% again, the PV unit will start tracking the load again. Here we have a planned islanding at the start of the 9th hour. We will start by increasing the P and the Q of the battery energy storage to unload diesel 1. Once diesel 1 is unloaded and the voltage and the frequency are within a certain limit, a disconnection signal is sent, and the battery energy storage system will start forming the grid for the PV-VFC. Here we have a reconnection scenario at the 21st hour. The power management system will start by turning on the active synchronization scheme of the diesel plant. Once the diesel plant is synchronized, the breaker will close and the battery will operate in a grid following mode and follows the energy management level signal again. We can conclude that the power management system designed for an off-grid power system consists of a diesel generation, PV, and battery energy storage system implemented on a SCL RTAG 3350 hardware could successfully navigate along the power dispatch schedule provided by the energy management system while adapting to the limitations of the units to attain a stable microgrid operation. The control hardware in the loop simulation setup implemented using RTDS real-time simulators provided a high flexibility environment to test the functionality of the power management system as setting up the IEC 61850 goose messages was expedient, and the competence of the IEC 61850 goose communication to facilitate the interaction between the hierarchical levels of the controller was validated. We would like to acknowledge the support of University of Manitoba, Research Manitoba, Schweitzer Engineering Laboratories, Protec Power Sales, and Solar Solutions. Thank you.
Hello, everyone. Thank you so much for joining us today. We are moving on to our live Q&A session. I hope you can hear me okay. We're having a little bit of inclement weather here in Manitoba. It's that time of year where we question ourselves why we live in this province. And I hope our audience is enjoying some nicer weather around the world. Thank you so much for all of your questions for our UNSW presenters. It is about 2 in the morning for them right now, so they are not here to answer those questions live. They are presumably asleep or perhaps partying in their RTDS lab, who knows? But we will make sure that your questions are answered in the Q&A document that we will send out next week. Now let's move on to a few questions for Dr. Rajapakse and Mr. Faraj from University of Manitoba. Perhaps we could start with you describing the kind of tests that were conducted to validate the PMS in the CHIL testing process. That's a question from Kalanath Katuri.
Hi, Katie. Thank you. So what we have done is that we had the energy management system that provide us with the forecasted data that should happen on site. We took this data and replicated inside the RTDS simulation over a 24 hours horizon with added noise and ramping it up and down, because what we get from the energy management system is like hourly data. We took that data and we also, what we have coming from the energy management level signals is also the optimal like reference signals for the diesel generator units, what should be enabled, disabled. For the battery energy storage system, also the power reference, and there is also a recommended PV power reference that we considered. So we took all of this data, we provided some of it to the SCL RTAG, and the generation and the load data, we took that and put it in the RTDS over 24 hours horizon. Then we ran the simulation over 24 hours and saw what kind of scenarios that the power management system has to took over the energy management system and take some actions, which was highlighted in my presentations. And also to test a certain functionalities such as emergency mode, SOC very low, we did conduct some of the scenarios that to see how to test that functionality, to target one of the functionality.
Excellent. Thank you so much for that comprehensive answer. I wonder if you could comment on whether there's a plan to deploy this microgrid physically in Manitoba, or perhaps it already exists in the province?
Yeah, so the system that we modeled is actually based on one of the remote communities in Manitoba. There is a PV system already there. It's a PV and diesel system, but there is no battery storage yet. And we were just studying like this possibility and then what we can achieve with that. So I'm not 100% sure whether there's a plan to include a battery yet. There's no solid plan. I think people are studying that. I think that's the situation as far as I know.
Thank you. All right, we have a question about black starting. Did you look into how the black starting of this network would be managed?
So in this research that we didn't look at the black starting with the battery energy storage system. We assume that black starting can be done with diesel because usually in these communities there is 2 or 3 diesel units because the power supply need to be very reliable because they depend on that. So even if one diesel unit is out, there are still other diesel units to start them. So we didn't look at black starting with the battery energy storage. I think it can be done. It shouldn't be a big problem depending on the load because already we have load shading schemes and everything implemented on the controllers. Yeah.
Okay, thank you. You mentioned in the presentation that 2 of the diesel units are run on grid forming control. Could you comment on how this control algorithm was implemented or what it was based on?
Yeah, sure. So what we have done is that we had the diesel generator model, and in asynchronous mode, you have to give it like a set points that is set to the nominal values, like 1 per unit frequency, 1 per unit voltage references. Whereas in a droop mode, what you do is that you add a after control loop to share the load between the diesel units based on the frequency and voltage measurements. And once you have a droop mode as well, you need to add a secondary control to bring back the voltage, the nominal voltage and frequency to restore it very slowly. Like that's basically what we have done. And you can find more information if you can like visit my thesis.
Okay, thank you. I wonder if you could discuss what hardware platform was used for the EMS.
For the EMS, in this research, we have used MATLAB, but typically, like in ideal situations, it would be another small ARCTAC to govern the power management system.
Okay, thank you. I think we have time for one more question. How much time did the controller take to send the commands using the Goose messaging communication? Did you measure that communication time?
Actually, we don't have like a accurate measuring, but roughly it was around 8 to 10 milliseconds. That depends actually on the variables as well, because Goose messages in RTDS usually associated with a dead band, right? But it shouldn't take
Yes,
much.
okay,
Like it
thank you.
didn't.
Okay, you know what? We have another question here before we wrap up. It's not quite 10 a.m. Is it possible to do this kind of CHIL for grid level BSS used for ancillary services and functions such as power shifting?
I think Professor can comment on that.
Yeah. It is possible to do that. Of course, in this case, we had to model the grid and the battery energy storage as required for that purpose. In this case, we modeled like the control functions that are needed for an isolated grid. But definitely, we can do control hardware and loop simulations to test a grid level battery energy storage system. I think that's the first presentation actually talk about this kind of.
Yes, exactly. And we also have a case study on our website that goes into San Diego Gas and Electric project in the United States, where they did some testing of ancillary services provided by grid level BESS. So that's something we have available as well. All right, I think that wraps up our question period. So thank you so much to our presenters for your time today, and thanks to our audience for your attention. We will look forward to seeing you at our next event. We are having a webinar next month about power hardware in the loop testing, and it will include a full demonstration, including some video of hardware. So that should be really interesting. It's not available for registration quite yet, but keep an eye on our website for the PHIL webinar that is coming up next month. Thank you so much again to our presenters from UNSW and U of Manitoba, and we will see you all next time.